Hello everyone, welcome back to my channel Shraddha's Physics. This video is based on statistical mechanics of the core 14. So today we will see what is blackbody radiation and its pure temperature dependence. So we have found that this is a perfect blackbody. So it means that a perfect blackbody, it absorbs all the radiations incident on it. So the blackbody is so called because the bodies which absorb incident visible light, it seems black to the human eye. In other words, a body will appear black if it absorbs all the incident wavelength and nothing is reflected back. As a blackbody is an ideal radiation absorber, it is also used as a standard for comparing all the absorptions of real bodies. When heated to a high temperature, the blackbody also emits the radiations of all the wavelengths ranging from 0 to infinity, and such radiations are called the total radiations. So a blackbody, it behaves as a perfect absorber as well as a perfect emitter. So the properties of a blackbody, they are not exhibited by any object in actual practice. Okay, a surface coated with lamp black, it can be taken to be a close approximation to the blackbody as it absorbs about 96% of the incident heat radiations. So Ferri in 1895 suggested a model as a hollow sphere with internal reflecting walls and a narrow hole opening in it. The diameter of this hole is negligibly small. So the Ferri's blackbody, it consists of a hollow sphere with an internal reflecting walls and a narrow hole opening in it. So the diameter of the hole, it is negligibly small as compared to the diameter of the sphere. If we heat this blackbody, that is, if the walls are at a high temperature, the hole will shine brightly because the radiations emitted by the blackbody. Because of this radiation emitted by the blackbody, these radiations contain all the wavelengths ranging from 0 to infinity and are known as the total radiations or the blackbody radiations. These radiations are homogeneous in nature and the energy density of this radiation is independent of the nature of the shape of the walls of the enclosure. However, these radiations, it depends on the temperature. All the bodies placed inside this enclosure, it also emit the blackbody radiations. Now we will see how the temperature depends, how the blackbody depends on the temperature, that is the pure temperature dependence. So let us consider a perfectly blackbody, it kept at the constant temperature, be placed inside a well insulated cavity of the arbitrary shape, having the walls at different temperature inside and outside initially. So the blackbody and the closed cavity, it will have the same temperature after some time. So under the equilibrium conditions, the blackbody, it emits the same amount of thermal radiation as it is absorbed. This quality and quantity of radiation inside this cavity, it depends on its temperature and its dozen temperature on the nature of the walls and the nature of the bodies present inside it. These are the two cavities, this is P and Q. They are having walls of different materials, they are filled with the radiant energy and they are kept at some temperature and are joined by a tube. This is the tube with the thermal radiations transparent screen S. This is the screen S. So the density of the radiant energy to be more in the cavity P than that in the Q. So here we are considering that there is an energy density difference. Okay. So the density of the radiant energy be more in the cavity P than that in the Q. So the greater amount of energy will now fall on the screen from P than Q. So in between these two cavity P and Q, so the greater amount of energy will now fall on the screen from P than Q. The radiation energy, so it will flow from P to Q till the equilibrium is attained. Since P has the more energy density than Q, so the radiation energy will flow from P to Q till the equilibrium is attained. After equilibrium, we separate the two cavities and they attain their new energy densities, that is the total radiation. Energy densities means the total radiations per unit volume, total energy radiations per unit volume. So the energy density in cavity P will be less than before so its wall will lose heat into the cavity and cool down until the thermal equilibrium is achieved again. Clear? So it means that when the equilibrium is achieved and we separate the two cavities, so they will attain the new energy density, and here you can see that the wall will lose heat into the cavity and cool down until the thermal equilibrium is achieved again. Now the energy density in the cavity Q is more than the before, and the wall of the cavity will absorb more energy from within and get heated. So it means that when we are considering that P and Q are both are having the different energy density, and and they are kept in the thermal equilibrium, and after that what will happen, the cavity Q will absorb more energy from within and it will get heated. Now the temperature difference in between the two cavities occur when they are at the same temperature. So it means that when they are at the same temperature, there will be the temperature difference. So without supplying extra energy from any other source, the temperature difference is set up between the two cavities P and Q. So it means that, so we are not provided any temperature or any external energy, so that here we can see that this temperature difference at the same temperature, so it contradicts the second law of thermodynamics. So here we concluded that the assumption that we have taken, that is the energy density P is more than that of Q, it is incorrect. So the energy density in P and Q, it must be identical in nature. Okay. Here the energy density of the radiation in a uniform temperature enclosure, it depends on its temperature and it does not depend on the nature of the walls. When some bodies are placed inside this enclosure having constant temperature, everybody will attain the temperature of the enclosure irrespective of its nature and the original temperature. So everybody inside the enclosure will radiate energy at the same rate. This emission of radiation will be exactly of the same kind as the cavity absorbs. Now we will see some important definitions, that is, first of all we will see the total energy density, that is U. Here the total energy density U, small u, this is U of the radiation at any point is the total radiant energy per unit volume around that point for all the wavelengths, that is 0 to infinity taken together. So this is the total energy density small u. Now we will see the spectral energy density U lambda. This spectral energy density for a particular wavelength, it is the energy per unit volume per unit wavelength. So that is U equal to, this energy density will be equal to U lambda d lambda over the limit 0 to infinity. So this is the spectral energy density is your U lambda and the total energy density is your U. Now see the total emissive power or emissivity, that is capital E. So it is the radiant energy emitted per unit time per unit surface area of the body for the all wavelength. This is known as the total emissive power. So it is the radiant energy emitted per unit time per unit surface area of the body for all the wavelength. Now the spectral emissive power, that is E lambda. This spectral emissive power at a particular wavelength, it is the radiant energy emitted per unit volume per unit surface area of the body within a unit wavelength range. It means that this is your small e lambda d lambda, this is E lambda d lambda integration over 0 to infinity, it is equal to the total emissive power. This is equal to the total emissive power capital E. For a perfect black body, this E lambda equal to maximum. It means that for a perfect black body, the spectral emissive power will be maximum. Now we will see what is absorptive power or spectral absorptivity. So this is the absorptive power of a body at a particular temperature, and for a particular wavelength, it is defined as, it is the ratio of the radiant energy absorbed per unit surface area per unit time to the total energy incident on the same area of the body in unit time within a unit wavelength range. So this is your absorptance equal to the thermal radiations absorbed A by a body in a certain time divided by the total amount of thermal radiations incident on the body at the same time. Now we will see what is reflectance. This reflectance, it is the ratio between the amount of the thermal radiations reflected by a body in a certain time to the total amount of incident thermal radiations falling on the body at the same time. So, this reflectance equal to radiation, that is capital R divided by Q. This is your thermal radiation. This is the thermal radiation of the body in a certain time, and Q is the total amount of incident thermal radiation falling on the body at the same time. Now, we will see what is transmittance. This transmittance, it is the ratio between the amount of thermal radiations it transmitted by a body in a certain time t to the total amount of thermal radiations incident on it at the same time. So, this is the transmittance. Transmittance is the radiation transmitted divided by the thermal radiations incident. This is the incident radiation. Now, the relative emittance. This is the ratio of the emittance of a surface to the emittance of a black body. It is called the relative emittance. This is your relative emittance. This is all about your black body radiation and its temperature temperature dependence, and there are some definitions related to your black body radiations. This is all for today. If you like the video, you can give the like and you can give your valuable comment, share and subscribe to my channel. Thank you.